The most common mathematical model used in statistics is a normal distribution. Let's learn some basic concepts about normal distributions. These distributions are sometimes called bell curves. Here's a histogram of a set of data for which a normal distribution model is a good fit. Notice the shape of this model is like the shape of a bell. Thus the term bell curve. Although you may have heard the term bell curve more than you've heard normal distribution, statisticians seldom use the term bell curve. They refer to normal distributions. Every mathematical model is a mathematical function. Functions are like machines. We put numbers into the function and numbers come out. The squaring function is an example. We put in the number 3, we get out the number 9, because 3 squared equals 9. When we look at pictures of a mathematical model, such as the normal distribution, it's simply the picture of a function. There is a mathematical function for the normal distribution. It's rather complex. So we should probably just look and say, "Ooh, that's nice," and leave it at that. To create the normal distribution, we put in a score from the horizontal axis, and the function will tell us where to plot our point along the vertical direction. This combination of inputs and outputs yields the curve that we call the normal distribution. There are some numbers in the function that we can change to get different normal distributions. These are called parameters. For the normal distribution, there are two parameters. They are the mean and the standard deviation. The mean and standard deviation are common statistics as well. To distinguish parameters from statistics, we use different symbols. Parameters are always symbolized with Greek letters. When we are referring to the mean of a normal distribution, we use the Greek symbol mu. When we are talking about the standard deviation of a normal distribution, we use the Greek letter sigma. Mathematicians set values for the mean and the standard deviation in the function, then input scores and get output to plot a normal distribution. We can readily identify the mean for a normal distribution because it is the highest point on the distribution curve. In this case, the mean is about 50. The standard deviation refers to how much variability or spread there is in the distribution. It's not quite as obvious to know what the standard deviation is when we look at the normal distribution. Let me give you some facts about standard deviation of a normal distribution that will help us out. We know that a certain percentage of scores in our distribution model are within specified standard deviations of the mean. If we look at all the scores between one standard deviation below the mean up to one standard deviation above the mean, this will include 68%, about 2/3, of the total number of scores. If we look within a range from 2 standard deviations beneath the mean to 2 standard deviations above the mean, this range will encompass 95% of the scores in the distribution. Finally, if we want to capture almost all the scores in the distribution, we can look at 3 standard deviations below the mean up to 3 standard deviations above the mean. This range will include over 99% of the scores in the distribution. To be more precise, it's 99.7%. So we will find almost all scores within 3 standard deviations of the mean. If we study our normal distribution example, we see that almost all scores in the distribution are in a range between 20 and 80. The score of 20 is 30 points below the mean of 50. The score of 80 is 30 points above the mean of 50. I know that this is about 3 standard deviations, so a standard deviation in this distribution must be about 10. That's because 3 times 10 equals 30, and taking the range from 30 below the mean to 30 above the mean captures almost all the scores in the distribution. With this information in hand, I know that the range from 40 to 60, that is 1 standard deviation below to 1 standard deviation above the mean, will capture 68% of the scores. If I look at the range from 30 to 70, that is 2 standard deviations below the mean to 2 standard deviations above the mean, this range will encompass 95% of the scores. There are at least 3 good reasons why normal distributions are the most common mathematical models used in statistics. Much of the data that we observe and measure in the natural world can be modeled with a normal distribution. For example, consider the weight of babies at birth. There is a small range of very common weights for babies when they are born. You'll sometimes hear of a baby's weight at birth and recognize it as being quite large or conversely quite small. These weights, however, are less frequent than weights that are near the mean weight for babies being born. This is true regardless of whether we're talking about human babies or baby sharks. Most babies at birth will have a weight near the mean weight. The further away the weight gets from the mean, the rarer its occurrence. Scientists often use constructs in their work. For example, we talk about the constructs of intelligence, motivation, self-esteem. Tests are created to measure these constructs. It's quite common to create these tests so that the scores follow a normal distribution. In this case, the normal distribution isn't occurring naturally, but rather the test or scale is designed to elicit data that will follow a normal distribution. Finally, a very important reason for using normal distributions is that they are theoretically important when we are making statistical inferences. I'm not going to say any more about that right now, but we'll save this for a future video about statistical inference. You'll then see how we rely on normal distributions again and again. Mathematical models are important in analyzing data, and the normal distributions are the most important of all mathematical models.